for the opportunity to share my vision for how we can have a sustainable future that involves the combustion of metals, and yes, I'm saying metals, as recyclable fuel that allows us to generate power when and where we need it with absolutely no carbon dioxide emissions. And so we're going to get this to go. All right, so we had a great introduction from Danielle there that was talking about the problems that are associated with our current energy system. And all of our energy right now, the vast majority, comes from fossil fuels. And fossil fuels are great from an energy perspective because they hold a lot of energy per unit mass. That's what we call the specific energy, and a lot of energy per unit volume, which is what we call the energy density. And that's why they're so useful to us as a society. But the problem, of course, is that when we burn these fossil fuels, we release carbon dioxide as well as a host of other pollutants into the atmosphere. And this carbon dioxide is causing climate change. So we need to look for alternative solutions. What we'd like to think is that we could just simply recycle carbon from the atmosphere. And this is the key idea behind biofuels, where the plants grow, pulling atmospheric carbon dioxide during their growth cycle. But the problem is that we can't produce enough biofuel sustainably to meet our energy demands, which are huge, as Daniel alluded to. We also might think that we're smarter than nature and that we can just extract CO2 from the atmosphere and produce liquid fuels out of that. The key challenge there is that to produce 1 liter of fuel was going to take us the carbon out of 3 million liters of atmosphere. And there's a huge energy penalty to be paid for doing that process. And so what we'd really like to find is some type of alternative fuel solution that enables us to deliver energy where and when we need it without the loss of that material to the atmosphere, without emitting those combustion products to the atmosphere, so we can recycle that fuel over and over again and enable us to take whatever clean primary power generation. We have plenty of hydroelectricity in Quebec. We can increase our production of wind and solar and use those then and deliver it to where and when we need it for, say, remote communities, for heavy-duty transportation, but also to sell that excess clean energy across the world as part of a renewable energy commodity. And so when we're looking for this, we've talked a lot about the solutions of batteries and hydrogen, and these don't fit the bill. We do not have enough energy density in typical batteries in order to replace fossil fuels. So those work very well for our cellular phones, for our laptop computers, maybe for light-duty transportation vehicles, but for very heavy-duty applications or for international energy trade, those are not going to work. We've also talked for a long time about the idea of the hydrogen economy. And hydrogen is a great fuel. It burns very well. We can react it in a fuel cell with very low pollutant emissions. And we can produce it using clean energy. But the problem is that hydrogen has a very low density, even as a cryogenic liquid. And while elemental hydrogen has an extremely high amount of energy per unit mass because it's a very light element, unfortunately, when we take into account the weight of the fuel system or the fuel tank, the energy density, the specific energy of that system is not so great. And so what our group is looking at is saying, well, if we look at the periodic table of the elements, what else is there? If we don't take hydrogen and we don't take carbon, what are the other fuel options? And so we've landed on the idea of using metals as a recyclable fuel. Metals have long been used as an energetic material inside of rocket propellants and inside of other energetic applications. For example, the space shuttle rocket boosters, the 2 rockets on the side of the space shuttle contain about 16% aluminum by mass. It's one of the main energetic components. And so we can burn these metals inside of flames. Here's some examples of flames that stabilize in our lab. If we make the particles very small, so about 3 microns to 10 microns, maybe even 100 microns in size, we can burn them inside of a flame. And in the case of aluminum, for instance, it's burning about 1,000 degrees hotter than the flame of methane or any other hydrocarbon fuel that we're used to. So there's a lot of energy here. And when we look at the energy density of the metals, because they're solids and they're quite energetic, it's extremely high. And they have reasonably good energy per unit mass as well. For instance, if we use lithium as a metal instead of a lithium-ion battery, the energy content is about 50 times higher. We can also react some of these metals with water and produce hydrogen and heat on demand where and when we need it. So instead of transporting hydrogen, we can create the hydrogen on demand. The way that happens is that metals will take the oxygen right off of water and release hydrogen as the combustion product. They want the oxygen even more than the hydrogen does. And so this is a picture from our lab of a set of images from a mixture of nanometric aluminum particles mixed with water, and that flame propagates down the tube. It produces hydrogen at over 3,000 degrees, and that type of system was used to launch a rocket called the aluminum ice rocket out of Purdue University, and our idea is to hook up that rocket to the front end of our engines and send that hydrogen into an engine to produce power or electricity. So our group is investigating the 2 main ways that we can extract energy out of metal fuels. The first is to directly burn them. In the combustion process, we produce heat. We can use that heat to produce energy in a coal-fired power plant retrofitted for use with metal fuels, for instance, or with advanced steam engines or Stirling engines. We can also react those metal fuels with water, producing hydrogen and on demand, and burning that inside of a diesel engine, a gas turbine engine, all the existing power systems that we've already developed, or fuel cells or other clean technologies that are currently under development. In both cases, the combustion product is a metal oxide, which is a solid, rather than carbon dioxide that's a gas that goes into the atmosphere, and that enables us to capture it and store it for recycling. So in both cases, we're going to capture those combustion products and circle it around. And so our vision for the metal fuel cycle is that where and when we have clean, sustainable energy, solar, wind, hydroelectricity here in Quebec, we use that to reprocess metal oxides, whether they're from the ore or the products of a reaction, into reactive metals. We can do that recycling process without any carbon dioxide emissions for some specific metals. Ship that metal internationally as a renewable energy commodity, use it where and when we want it for power generation, and have absolutely no carbon dioxide emissions at any point in the cycle, but still take advantage of all of this infrastructure that we've developed for fossil fuels. Thank you.